All right, let's dive into a question that sounds so simple you'd think a kid could answer it. But the real answer? Oh, it completely flipped our entire understanding of the universe on its head.
So really, what is heat? I mean, think about it for a second. What's the first thing that comes to mind? You feel it every single day, right? That hot cup of coffee, the cold air outside. It seems so obvious. But, well, our gut feeling here is actually a little bit off.
You see, heat is not fire, that's for sure. It's not just energy, at least not in the simple way we usually think about it. And here's the real shocker. It's not even the same thing as temperature. Yeah, they're all connected, but none of them get to the heart of what heat really truly is.
The real answer is this. Heat is chaos. It's pure, unadulterated disorder. It's the messy, random, totally disorganized dance of trillions and trillions of microscopic particles. And getting our heads around this one idea, thanks to the absolute genius of Ludwig Boltzmann, didn't just explain what heat is, it changed the game for physics forever. Okay, you have to hear how this happened.
So to really get why Boltzmann's idea was such a bombshell, we need to hop into time machine and go back to the 19th century. Because back then, scientists had a very, very different picture of the universe.
You know, thanks to Isaac Newton, everyone thought the universe was basically a giant, flawless clock. Every planet, every rock, every little particle was just another gear in this perfect machine, following these incredibly precise and predictable laws. I mean, if you could just know the position and the speed of every single particle, in theory, you could predict the entire future of everything. It was neat, it was tidy, it was perfect.
But there was this one huge, glaring problem they couldn't ignore. Heat. Heat just didn't fit. It didn't play by the same clean, reversible rules. Heat was messy, and it always seemed to stubbornly go in only one direction. And for that, classical physics had, well, no good answer.
I mean, think about it. A hot cup of coffee on your desk always cools down. An ice cube in a glass always warms up and melts. The heat flows from hot to cold every single time. It never ever goes the other way. But why? In a perfect clockwork universe, shouldn't you be able to just run the clock backwards? Why is heat stuck on a one-way street? This super simple, everyday thing was actually a deep, profound mystery.
And this is where our hero, Ludwig Boltzmann, steps onto the stage. He came along and proposed something so out there, so radical for his time. He basically said, look, to understand heat, you've got to stop thinking of the universe as a perfect machine. You need to start thinking about it in terms of atoms and chaos and, get this, chance.
So Boltzmann's first big idea was this. What we feel as temperature isn't some mystical property. It's just a measure of the average speed of countless tiny atoms and molecules all jiggling and bouncing around chaotically. A hot thing is just a thing where its atoms are on average vibrating and zipping around way faster than the atoms in a cold thing. That's it. And heat then isn't some invisible fluid or substance. It's just the process of transferring all that chaotic motion from one place to another. When the superfast particles in a hot object smash into the slower particles of a cold object, they pass along their energy. The fast ones slow down a bit, the slow ones speed up a bit, and that transfer of energy is heat. But this led him to his most incredible insight. The laws that govern this whole process, the laws of heat, weren't like Newton's laws. They weren't absolute and precise. They were laws of probability. It wasn't about what has to happen. It was about what is just overwhelmingly likely to happen. And that, well, that changed everything. Now, to really wrap your head around this idea of probability, Boltzmann used a concept that is famously tricky, but it is so important. Entropy. The simplest way to think about it is just as a measure of mess, a measure of disorder.
Okay, so entropy has this really cool two-part definition. On the surface, the big picture, it's just a measure of chaos. But if you zoom all the way in to the microscopic level, it's something way more specific. It's literally a count of all the different ways you can arrange the individual atoms and molecules in a system and still have it look the same on the outside. The more ways there are to arrange things, the higher the entropy.
Let's make this super simple. Imagine a box with a wall down the middle. On one side, we put one kind of gas, and on the other side, a different kind. See how neat and tidy that is? This is a very ordered, low entropy state. And why is it low entropy? Because there's basically only one way to arrange the particles to get this look. All the X guys on the left, all the triangle guys on the right. Statistically speaking, this is a very improbable setup. So what happens if we pull out that wall? Well, you know what happens.
The particles, in their totally random, chaotic motion, are going to start mixing together. And pretty soon, you have a completely disordered, high-entropy state. But here's the million-dollar question: why? It happens because there are just astronomically more ways to arrange the particles in a mixed-up mess than there are to have them perfectly separated.
And this gets us right to the core of Boltzmann's genius. The universe doesn't have some secret desire to be messy. It just settles into whatever state is the most probable. The state with the highest number of possible arrangements wins. That mixed-up state isn't better or more advanced, it's just mind-bogglingly more likely to happen just by pure random chance.
And this whole mind-bending insight gets boiled down into one of the most beautiful and powerful equations in all of science. It's an equation so important, it was literally carved onto Boltzmann's tombstone.
There it is, S equals K times the natural log of W. It looks so simple, doesn't it? But what it does is connect two completely different worlds.
So let's break it down. S is entropy. That's the big picture thing we can actually see and measure, the overall messiness of the system. W is the thermodynamic probability. That's the gigantic number of all the possible microscopic ways you can arrange the tiny bits and pieces. And K? That's just a special number, the Boltzmann constant, that acts like a bridge, connecting the tiny world of atoms to the big world that we actually live in. This little equation is the bridge between those two worlds.
The elegance of this idea just captivated physicists for generations. I mean, the great Erwin Schrödinger, one of the fathers of quantum mechanics, he was just in awe of what he called the pure, inexorably clear sequence of Boltzmann's thought.
And here it is. This is the big, profound takeaway. The famous second law of thermodynamics, the one that says entropy always increases, that heat always flows from hot to cold, it isn't some unbreakable absolute rule like F equals ma. It's a statistical law. I mean, could all the air molecules in the room you're in right now suddenly decide to rush into one corner and leave you in a vacuum? Technically, yes. Is it going to happen? No way. The odds are so infinitesimally small you'd have to wait trillions of times longer than the age of the universe just to see it happen once.
So let's go all the way back to our cup of coffee. Why does it cool down? It's not because of some magical cooling force. It cools down because the state where all that energy is evenly spread out between the hot coffee and the cooler room, that messy, mixed, high-entropy state, is just vastly, overwhelmingly, stupendously more probable than the state where all the fast-moving particles just decide to stay put inside the cup. It's not a rule. It's just a statistical inevitability.
And that leaves us with this incredible, lingering question. Boltzmann's revolution suggests that the order we see all around us, maybe even the forward direction of time itself, isn't written in some unbreakable law of certainty. Maybe it all just emerges from the raw, brute force statistics of chaos. It really makes you wonder, is our universe a perfect clockwork machine after all? Or is it just playing the odds and winning every single time?